with where we left off. Okay, let me back up one page. Here is when we're dealing with ionic compounds, and not necessarily ionic compounds, but the other ones that are covalent too. We'll get more on that here in a bit. That the net charge is going to be a 0. So we're going to have to add enough cations and enough anions. So when we put them together, the total charge is equal to 0. And in that example, we had sodium that is a +1. And we had the nitride, which is a -3, excuse me. And therefore, we need 3 sodiums to counter the -3 charge of the nitride. So the formula for sodium nitride will be Na⁻3, and then obviously the nitride, or N for nitride. Okay, here we had sodium, again with the sulfur ions. So we got to go to the periodic table, find what the ion charge for sulfur. It is in group 6, okay? And therefore, sulfur when it becomes an anion, because it's a nonmetal, it's going to gain electrons, as a -2 charge. Sodium we know is in group 1, and therefore we need 2 of them, 2 sodiums. So it's sodium subscript sulfide, and the name being sodium sulfide. Magnesium is a +2. Oxygen, which becomes oxide, is a -2. And so we can put those together as a 1-to-1. So therefore the formula will be MgO. So magnesium oxide, okay? Potassium, +1. Phosphorus, which becomes now phosphide because it's the ion, as a -3. We need 3 potassiums. And then we did talk about this one where we have calcium, which is a +2, and a nitride, which is a -3. And so you really can't put them together, 1-to-1, obviously. And so you got to find a common number, and that common number was 6. So we need 6 positives and 6 negatives. And that gives us that combination where we need 3 calcium and 2 nitrides for them to come together to create the neutral ionic compound, and the name would be simply calcium nitride. Okay. Aluminum has a +3. Chlorides, being in group 7, have a -1. So we need 3 chlorides per each aluminum ion, which has a +3. So we got AlCl3. And then zinc always has a +2. The iodide, again, also like being a halogen, we have a -1. We need 2 of them to have zinc iodide. Now, the Roman numerals. Now, the important thing to remember, because I had a couple of questions on this with respect to the homework and quizzes and so forth, is remember I talked about the Sweet 16, I call it that, simply because those were the metals in group 1 and group 2, and then I gave you aluminum, zinc, silver, and cadmium, and I gave you the charges. Those 16 always have a known oxidation number or charge, okay? And so for those 16, we don't have to put a Roman numeral. That means that all the other metals require a Roman numeral. Why? Because their oxidation state or charge can vary. Copper, in this example, can exist as a +2 or a +1. So you have to be told, okay, you're going to use copper 2 Roman numeral. The question I was asked, well, can we put the regular number 1, 2, and 3? No. And the Roman numerals are used specifically to designate the oxidation number of these other metals, okay? So make sure you use the Roman numeral. So this tells you copper 2, we're dealing with copper +2. And oxygen, which we know is oxide, when it's an ion, is a -2. So we can simply put them together as a 1-to-1, okay? And therefore, if we were to name this compound, it would be called copper, C-O-P-P-E-R, Roman numeral 2 in parentheses oxide. Here again, the lead not being part of the 16 requires an oxidation number, and they're telling you it's a +4. Oxide is a -2. We need 2 oxides to counter the +4 of the lead +4. All right, so every time you put the metal and nonmetals together to make ionic compounds, check the charges, make sure that they all add up to 0, okay? And then if you need more of one or the other, that's where they become part of the subscript. All right, so the polyatomic ions, we talked about this from the periodic table, okay? Those are found in the periodic table in the left-hand corner. Those are ions that you keep together as a unit. So in this case, you have the magnesium ion, which would be a +2, and then you have the OH, and this is where you refer to the periodic table. If you look that up, that's called the hydroxide. Now we keep the name hydroxide. Okay, so together we're going to call this magnesium hydroxide eventually. But notice that the hydroxide has a -1 charge for the whole unit, for the oxygen and the hydrogen, okay? The magnesium has a +2 charge because it's in group 2. So we need to put them together. And since we need more than one hydroxide, we put a parentheses around the whole unit, the whole OH, and put our subscript. And hence we write it like this: magnesium parentheses OH and parentheses subscript. So that tells you that you have 2 hydroxide ions, which are the polyatomic ions. This one, the PO4 -1, is called the phosphate. Again, I direct you to the table. Okay, that whole unit has a -3 charge. And just like the nitride, which had a -3 charge, it requires a total of +3 to counter its charge. Potassium, we know, is in group 1. So therefore, the ion of potassium would be a +1. So we need 3 potassiums to counter the charge of -3 from the phosphate. And here we don't need a parentheses around the potassium. We simply put the subscript. Okay. So we just put potassium, K subscript 3. We don't need a parentheses around the PO4 because you only need 1. Okay, it's understood. It's 1 unit. Here we got silver. Okay, silver is one of those ions that have the +1 charge. It's one of the constants. And then that SO4 has a -2 charge for the whole unit. That is called the sulfate. It's in your table. And so that you can see it, silver has a +1. And we need 2 of them to counter the -2 of the sulfate. So we write the formula, silver Ag2 and then SO4. Okay. So far the naming on top. Let me do this real quick. This one right here would just be magnesium hydroxide. Okay. Right here, potassium phosphate. The name we get from the polyatomic ion. And this one here, the next one, silver sulfate. Oh, yeah, do check your spelling. Sulfate. Now, notice we didn't use the Roman numerals here because all of the metals are part of the 16. So we don't require Roman numerals here. Okay. Now we got calcium, and NO3 is called nitrate. Okay. Oh, yeah, nitrate. So that one would be called calcium nitrate. Okay. Now we got a metal with a Roman numeral. which tells you you're dealing with copper 2 plus 2. Okay. The CO3 is the carbonate. Sodium, so in this case, it's called copper 2 carbonate. And since both of them have got a plus 2 and a negative 2, it's simply a 1-to-1. Okay. And so let me do the name here. This is calcium nitrate. Okay. The next one, copper, Roman numeral 2 carbonate. Okay. The names in the formula for the polyatomic ions, again, are given to you in the periodic table. And I'm writing the names because right now we're making the formula. Eventually, we're going to start naming them. And so be able to go from the name to the formula or vice versa. Okay. Next one. Okay. Well, I thought I had one more. So remember to use the parentheses when you need to add more than one polyatomic ion. Okay. Like we did with the calcium nitrate and the magnesium hydroxide. All right, let me get rid of that. All right, so now that we can write the compounds, we need to learn the names, which I started to introduce you to it, okay? The name depends on whether the metal has a fixed or variable charge. And you already know about the fixed charge. Those are 16 of them. The variable, well, you may not know what it is, but you're always going to know the partner. You're always going to know the charge of the cation or the anion. And knowing the fact that you have to add enough of each equals 0, you can figure out what the partner's charge is. Okay. All right. So we'll do some examples of that. So we already discussed the variable oxidation numbers and using Roman numerals. Okay. Now, I've also talked to you about when the nonmetals become ions. When, example, chlorine became an ion, again an electron, an anion, we changed the name to ide, chloride. And that would be true for all the halogens, fluoride, chloride, bromide, iodide, okay? Oxygen becomes oxide. I'm going to the next group 6. Sulfur becomes sulfide. Nitrogen becomes nitride, and below nitrogen is phosphorus, and that becomes phosphide. And if you ever see carbon that gains 4 electrons, because carbon's in group 4, guess what? Its name would be carbide. Okay. All right. So this name here, Na, good old-fashioned table salt, we will call that sodium chloride. That would be incorrect to say sodium chlorine, because chlorine is the element, not the ion. And we're talking about ionic compounds. So everybody, cation and anions are all ions. Okay? Let's get the name of this. Now, you see K, obviously you got to remember what the name is for K, which is potassium. Okay? And you can see Br, which is bromine, and you might think, oh, okay, this is bromine. But remember, it's bonded next to potassium. It's attached, written with potassium next to it. That infers that it is bonded. And if that's the case, then it's ionic. Therefore, bromine becomes bromide. So that would be called potassium bromide. Okay. Again, we have magnesium. Notice that the metals, we don't change the name. Potassium remains potassium, whether it is element or ionic, or cation in this case. Okay, magnesium stays magnesium. If we needed to distinguish between magnesium atom or element or magnesium ion, that's what we add. We'll add the term atom or element, or the term ion, okay? Whereas with the anions and nonmetals, just by the name automatically tells you if you are dealing with either the element or the ion. Magnesium, and so oxygen becomes oxide. That is magnesium oxide. Now you can mix and match here. Okay, so far we've done potassium bromide, but you can partner up with oxide and make potassium bromide oxide, or you can take the magnesium, partner up with bromine or bromide and make magnesium bromide. Okay, or any of the halides, chloride, iodide, or oxide, or nitride, or phosphide. So you can see you can start building a library, if you will, of all the different compounds just by mixing the cation and the anion and putting them together in the right ratio. Here we have calcium. You see fluorine at first, and you see the subscript, you might want to think fluorine, but remember you got calcium right before it. That tells you it's bonded. It's an ionic compound. So we're not dealing with fluorine, the diatomic element. You're dealing with fluoride, hence calcium fluoride. Okay. Lithium, sulfur becomes sulfide. So now we got lithium sulfide. Notice we're not using any Roman numerals here. Also, another factor to remember, like we just did lithium sulfide, there are no prefixes. Like we didn't say dilithium sulfide. We just said lithium sulfide. When we get to the covalent compounds, and there only for covalent compounds, we'll be doing prefixes like carbon dioxide, carbon monoxide. Okay. But all ionic compounds, just put this in long-term memory, do not use the prefixes of di, tri, quad, whatever, penta. We will get to those prefixes, okay? So no prefixes. Silver chloride, okay? And notice here, you can take the first one, potassium bromide, combine it with potassium oxide, potassium fluoride, potassium sulfide, potassium chloride, and every other combination that you can think of right there for these five. Okay, so no prefixes like mono, di, tri, etc. for ionic compounds. Okay, so that would be incorrect for number 4 if you were to write in dilithium sulfide. Okay, that is not the accepted name for that compound. And these names are accepted names not for our class, but for the world. There is an organization called, there's an organization that keeps track of naming compounds, and so that we're all consistent, whether we're dealing with chemistry here or on the other side of the world. Chemists would use the same nomenclature throughout. Okay. All right. So when we're dealing with the polyatomic ions, this is where it takes a little practice, okay? Because you look at that NaNO3, it's a matter of practice and recognizing that you're dealing with nitrogen and 3 oxygens combined. So hopefully that would trigger your memory and say, I am dealing with a polyatomic ion, okay? Especially when there are no parentheses around it. If you see a parentheses, that right there would tell you I got a polyatomic ion, then you refer to your table. And so here, first example, you got sodium nitrate. Okay. Now here we got potassium, and then we see PO4. Okay. PO4 is a polyatomic ion, which is phosphate. Okay. And the cation is potassium, so its name would be potassium phosphate. Okay. Here's a parentheses. Parentheses should trigger something. Say, hey, I got a polyatomic ion. The OH. So go to your table, find the OH, find its name, and you'll find it to be hydroxide. Now, Ca is simply calcium, so now we have calcium hydroxide. No, we didn't, because we have 2 hydroxides. Notice we did not say dihydroxide, just simply hydroxide. You'll find a lot of naming stuff out here in the real world. For whatever reason, they used to call use the prefixes. So if you read the labels, you'll see a lot of misnaming of compounds. You occasionally will see calcium hydroxide here. You might be familiar with calcium hydroxide. If you ever take Tums for an upset stomach, that is what you are ingesting, calcium hydroxide. Okay, and because the hydroxide is a base, and we're going to talk about that next chapter. Okay, SO4, recognize that as a polyatomic ion. That's called sulfate. Okay, Zn is zinc, so its name will be zinc sulfate. Now, the examples we did so far, we dealt with the metals that have a non-variable oxidation number, those 16. Okay, now we're going to be dealing with the other metals, the ones that have a variable oxidation number. Okay, and so the format here is take the metal, then in parentheses the Roman numeral number, which pertains to the oxidation of the metal. It has nothing to do with the nonmetal, but all we do with the nonmetal is take off the suffix and add IDE. Okay, and so you're given this and you're thinking, okay, I got Cu, which you recognize as copper. Okay, next question to ask yourself, okay, copper, is it part of the 16? The answer is no. Okay, that means I got a variable. So how do I know what the charge is? Well, then you look at the chloride. You know that the chlorides are -1, and you got 2 of them. That tells you that copper must be a +2. Therefore, its name would be copper, Roman numeral 2, chloride. Okay. So this is a good example of, you may not know what the charge is of the metal you're given or the nonmetal, but you always know the charge of the partner. And so in this case, you know the charge of the chloride. And you also know from the equation it gave you that the number of cations must equal the number plus the number of anions must equal 0. In this case, because it's a neutral compound, and you got 2 of them, each one's a -1, copper must be a +2. Therefore, its name is copper, Roman numeral 2. Okay. How about this one? Here we got Pb, which is lead, and then we got oxygen. Again, lead is not one of the variable atoms, and so we have to determine what the charge is. Oxygen has a -2 each one. There's a total of 2 of them. So that tells you there's a total of -4 charge coming from the oxide. And you want that equal to 0. So lead must be a +4. Okay. And so we use a Roman numeral, the name lead, parentheses IV. Okay. And do put those in caps, which IV is 4. So the name is lead 4 oxide. Okay. All right, we got nickel and we got Br, which is the bromide. And we got 3 of them. And so I don't know what nickel is, but we need to calculate it. I do know what the bromide is, right? Because it's in group 7 and ionic bromide is -1. There's 3 of them, 3 bromides. That should tell you that nickel is a +3. And so it's nickel, Roman numeral 3, bromide. Okay. All right. Here we have this one, Mn, manganese. We got SO4. This is a polyatomic ion. Okay. And you again refer in the beginning, you refer to your polyatomic ion table, but eventually with time you really get the hang of it and you recognize it pretty quick. But that SO4 or the sulfate is a -2. That infers that manganese must be a +2. So we write it as manganese, Roman numeral 2, sulfate. Okay. Again, we're dealing with a polyatomic ion, NO3. Excuse me. In this case, it's nitrate. Okay. Copper and nitrate has a -1 for the whole polyatomic ion. That tells you that copper must be a +1. So it's copper, Roman numeral 1, nitrate. All right, CO. CO is cobalt, okay, and is bonded simply to nitrogen all by itself. So that is nitride, okay. Notice that number 4, we had nitrogen, and right immediately following nitrogen, you see oxygen. That's a flag for you to tell you that's a polyatomic ion. But in this case, it's simply nitrogen all by itself. So it's not a polyatomic ion, it's just simply the ion of nitrogen, which in this case is nitride. Okay, it's in group 5, so it has a -3. That tells you cobalt must be a +3. And therefore, we write it as cobalt, Roman numeral 3, nitride. Thing to remember is be able to go in both directions. Okay, given the name, write the formula, etc., etc. All right, and that's why I drew those double arrows there. So let's move on here. Oh, got one more. Sorry about that. All right. Now, we have an interesting thing here. You see Fe, which hopefully by now you know the name of that is iron. Iron is not of the 16, so it's a variable oxidation number. The question is, all right, what is its charge? Okay, well, if we go to the polyatomic ion, because those parentheses around CO3 should say to you, I got a polyatomic ion. And if you look that up on that table, it would be the carbonate ion, okay, which has a -2 for the carbonates. And there's 3 of them, okay? So that means there must be a total of -6. So let's do it this way. Let me write something here real quick for this last one. Okay, we see we have 2 irons. Everybody agree on that, right? All right. Then from the parentheses, we got 3 carbonates. 3 carbonates. And the carbonates from the polyatomic ion table are each -2. And so therefore, all that must equal 0. So we basically set up an algebraic equation, okay? So if we take, rearrange this, we get 2 iron is equal to a +6, right? Because I took -2 times 3, that's a -3. I moved it over to the right side of the equation. It becomes a +6 because I got to add -6 and +6 on the left. I got to add +6 on the right. Okay. Now, if I divide through by 2 and solve for iron, my iron must equal a +3, right? Because dividing 6 by 2, that's a +3. So that tells me that I am working with iron 3. And the CO3 is a carbonate. So the name of this compound has to be iron 3 carbonate. Okay. Now, when we were talking about the variable ones, remember we were combining them, where we were looking for a common number, and in the examples we did was 6. Well, in this case, this also is a common number is 6. But you can very quickly, by looking at that formula, remember I said that the charge of the anion becomes the subscript of the cation. Now, CO3 has a -2. Look at the subscript for iron, that's a 2. That infers that the subscript for the carbonate 3 has to be for the iron. So we can just glance at that and determine that you're working with iron 3, simply because the subscript of the anion represents the charge of the cation. Okay, if you don't see that, then work the problem through like we did over here by setting up a little equation. All right. Let me clear this. All right, so we have strontium and hydroxide. I'm going to go ahead and give you the answers here. Strontium is in group 2, okay? The OH is hydroxide from the polyatomic ions. So strontium is in group 2, its cation its charge is +2. That means that we need 2 hydroxides to counter the +2 of the strontium, okay? Number 2, they're asking you just simply for the name. Well, AU is gold, okay? AU is gold, and it's not part of the 16. So we need to calculate what its oxidation number is. So we look at the partner, the anion, which are chlorides. There's 3 of them. That must be gold 3, okay? Zinc, we know it's a +2. Oxide, always a -2. Simply put them together 1 to 1. We get the formula of ZnO, or zinc oxide. Okay. Barium phosphate, number 4. Phosphate, PO4, is the polyatomic ion from your table. Barium is in group 2, so it has a +2. So here we have a mismatch. We got a +2 for the barium and a -3 for the phosphate. So we look for a common factor. Again, in this example, the common factor is 6. So that means we need 3 bariums and 2 phosphates. Okay, so we can put them together in the correct ratio. Okay, but notice that the superscript, and let me see if I don't know if I can use that. The superscript of, oh, that's a big one. That's a bad one. The charge of the phosphate became the superscript of the cation. Okay, let me clear that big old thing. And the charge of the metal became the superscript of the anion. I don't know why that thing is so humongous. All right, so we got barium phosphate. We got lithium. Now be careful, because there's SO3, which is polyatomic ion, but there's 2 of them. There's an SO4 and an SO3. The SO4, okay, is called the sulfite. The parent name sulfate, SO4, when it has 1 less oxygen, the ATE, 8, becomes ITE. The same is true for nitrate, NO3. There's also NO2, so it goes from nitrate to nitrite, okay? But they're in your table, you can see the trend there. And so you're here, it's SO3, and so it's the sulfite. Lithium has a +1. Sulfite has a -2. And therefore, we need 2 lithium. So we got La2 and then SO3, or otherwise known as lithium sulfite. Aluminum and sulfur, which is sulfide. We got a mixed match again. Aluminum is a +3. sulfide is a +2. We find a common number. And so the formula is Al2S3, okay? Or aluminum sulfide, okay? Notice with number 5, you got SO3, you got sulfur, and then immediately after that is oxygen. And that right there should tell you, polyatomic ion. Number 6 is just sulfur all by itself. So just the element all by itself in ionic form, which makes it sulfide. All right. And then the last one, they're asking you to just name it. You got Cu, which is copper, has a variable oxidation number. We need to figure out what it is. And then we have in parentheses NO3, which is the nitrate. And so you go to your table, NO3 has a -1 charge. And there's 2 of them. So there's a total of -2 that infers that copper must be copper 2. Okay. So it's copper 2 nitrate. Give the formula here. Well, we got sodium, which would be Na. So I would write these first. When you're given names, write the ions first, okay? And so we know that, let me see here, before you put these together, you write the ions. So we know that sodium is a +1, correct? And then nitrite, if you look at the periodic table, that's NO2. And it's got a -1. Okay? And so we're asking you to write the formulas. First, put them in ionic form. Why do you want to do that? Because that way you can make sure that you put enough of each together. Okay? And since sodium is a +1 and the nitrite, is a -1, we can simply just put them together, 1 to 1. Okay? And we end up with NaNO3. Okay? Nickel, 3, Roman numeral 3. So we start right down nickel +3. And then oxide, you know, that's a -2. So we got a +3 and a -2. Find a common number, which is 6. So we need 2 nickels and 3 oxides. Okay. Magnesium iodide, write the ions. Magnesium is a +2. The iodides are -1. I need 2 iodides. Okay, for the +2 from magnesium. So it becomes MgI2. Aluminum cyanide. Well, cyanide is one of the polyatomic ions from your table, and it has the structure of the formula of Cn with a negative. Okay, and we know that aluminum is a +3, so we need 3 cyanides to counter the +3 from aluminum. Hence, we use a parentheses. Okay, don't put a subscript on the carbon 3 and put a subscript on the nitrogen, because that is not cyanide, that is something else. Remember, those are polyatomic ions, and if we need more than one, you put a parentheses around it, okay, and use a subscript in that parentheses. Okay, which kind of brings us to covalent and molecular compounds, okay? No metals involved here, just nonmetals, okay? There's really no, they're not ions, so there's no charge in general. This is kind of iffy, but the naming remains the same. You know, whether we use, let's say, sodium oxide or we use carbon monoxide, the name of the anion still is changed to the IDE. Okay, but we use prefixes. Again, this is important. Only for covalent or molecular compounds do we use prefixes. And these are the ones we use: mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and octa for 8. They do go up to 9 for nona and deca for 10, but we're going to stick to with the 8. So those are the prefixes, okay, that we utilize. So the format, the nonmetal name, normally the first element you should see is the central atom that you be written in that form, okay? And then if there's more than one of those, you put a prefix and then the nonmetal name, okay? And then followed by a prefix if you have more than one of the nonmetal name of the next one. But we also maintain the IDE format. So carbon dioxide, okay? If it was C2O2, there isn't a compound like that, but if there was, it would be dicarbon dioxide, okay? We'll do some examples here. If it's just the first metal by itself, like carbon dioxide, we don't use the mono, so it's just simply carbon, okay? But if it's another one by itself after the central atom, then we use mono, hence carbon monoxide, okay? CO, capital O, is carbon monoxide. CO2, carbon dioxide. You see how that works? All right. Carbon dioxide, we just talked about that. All right. Now, it's CO, it's carbons first. Normally, the first element is the central atom, and then whatever follows is bonded around the central atom. The only exception is H2O. By convention, if people write it H2O, hydrogen is not the central atom. Oxygen is, okay? That's really the only exception that you'll see. We see carbon and we see one oxygen, hence we use the prefix monoxide, okay? Here we have the parent name. First, look at the parent name. We got phosphorus and oxygen. Phosphorus is the central atom, okay? And then oxygens are bonded around it. There are 2 phosphorus, so we're gonna have to put a prefix on that. And there are 5 oxides, so we got to put a prefix on that. So this name is called diphosphorus, okay? Pentoxide. Notice that we didn't say phosphide. Why? Because it's written first, and that's the central atom, so we keep the name of the element, okay? So it's, and this, the way it's written is phosphorus and not phosphide, totally different. If the phosphorus came afterwards and we were using it further, to the right of the central atom, yes, then it would be the IDE. Okay, here's another example. We've got phosphorus by itself. We don't need the mono, it's the first central atom, so just phosphorus. And then we got fluoride. And there's 3 of them. So the parent name is phosphorus fluoride, okay? Once I figure out the parent name, now I go and add the prefixes, okay? So in this case is phosphorus trifluoride, okay? This example, look at the parent name first, look at the elements involved. We got iodine in the first, so it's a central atom, and then we got 7 fluorides. So the parent name is iodine fluoride. Now you go back and add the prefixes. Well, there's only 1 iodine, so we don't put a prefix, and there are 7 fluorides, so we add the prefix of hepta. So iodine heptafluoride. All right, and here same scenario with the ionic compounds. You can be given the formula or given a name. You need to go one way or the other. All right, so here we have this. We have this compound. First thing to do, my suggestion is to first write the base name. Okay, Don't worry about the prefixes right now. Just get the base name. We see BRs up front. That's the central atom. And so that's bromine, since it is up front. If it was after the fact, then it would be bromide. But it's the very first guy, bromine. Okay? Then we got oxygen bonded around the bromine. So its name is still oxide. Okay? So that is what I mean by the parent name, bromine oxide. Now go and add the prefixes. There are 3 bromines, so it becomes tri. Okay? And there's 8 octoxide. I believe it's the A. There's some English, I forget the rule, I'll look it up. If it's a vowel, precedes a vowel, you leave the A or you don't take out the A. If you leave the A, I'm not going to count it off. It's fine. Okay, because, so find the parent name, add the prefixes, tribromide, octoxide. Let me get rid of that. Okay, next one. Phosphorus and sulfide. Parent name, phosphorus sulfide. There are 4 phosphorus and 7 sulfides, hence tetraphosphorus heptasulfide. Next example, we got 1 sulfur, 3 oxides, sulfur trioxide. Nasty smelling gas. Okay. Now you're given the name and they want you to work backwards and write the formula. Okay, so they write iodine, find the formula for iodine, which is I, and then the prefix is hexa, which means there must be 6 of them, and then there's fluoride, so that's F. So there are 6 fluorides in 1 iodine. So the formula would be IF6, subscript 6. Okay, dichlorine pentoxide. Okay, so the base formula is chlorine and oxygen, the O, Cl and O. Then the prefixes, we got 2 chlorines and 5 oxides. Hence, there's the formula, dichlorine pentoxide. Okay, now we have, they want you to get the name, they give you the formula. All right, so you figure out the parent name. We got phosphorus is the very first atom, so its name stays phosphorus. And then you got iodine, which is iodide, because it follows the central atom. And then we get the prefixes. There's 2 phosphorus and 4 iodides, hence the name diphosphorus tetraiodide. It's a little tongue twister. All right, remember a couple of reminders. Prefixes are only good for covalent compounds. Don't use them, okay? Don't use them for covalent compounds. Let me restate that. Don't use prefixes for ionic compounds, only for covalent compounds, okay? Always use Roman numerals for those metals that have variable oxidation states. And 16 of them that you always know 100% of the time the oxidation state. Those don't require Roman numerals, okay? Because those are constant. And polyatomic ions, when you try to name them, no, you don't. They each have their own name. So SO4, the sulfate, would not be sulfur tetraoxide, something like that. No, it's just sulfate, okay? That doesn't change its name. Each polyatomic ion has their own individual name. Okay, you might want to try these at home, but we can go very quickly. We got barium chloride, okay, nitrogen dioxide, just like carbon, replace the carbon with nitrogen. Now you got nitrogen dioxide. We got iron phosphate, specifically iron 2, okay, because the phosphates are each -3, and there's 2 of them. Okay, so our common number is 6, so that means we need 3 irons because each one is a +2. And then we have diiodine tetroxide, that would be I2O4, silver sulfate, okay, which would be Ag2SO4. Why Ag2? Because the silver has a +1 100% of the time. Sulfates from your polyatomic ion table is a -2, so we need 2 silvers, silver sulfate. And then nickel 3 sulfide. All right, nickel 3 tells you write the ions. Nickel +3 is the ion. Sulfide, the term IDE means just sulfur by itself, unlike number 5 where it says sulfate. Okay, the AATE should tell you polyatomic ion. The IDE tells you single element, the single sulfur, which has a +2, so we need to combine them, unequal charges. So we got to find a common number. So the formula is Ni2S3. Okay. That really, now don't forget we got worksheets on this. Make sure you do them as as much as you can. Practice makes perfect. As far as naming them, and if you have any trouble or questions, by all means, shoot me an email. All right. I still got a few minutes here. Let me at least start with chapter 9 real quickly. We'll finish this up on chapter 9 on obviously on Monday, but it's a relatively short chapter. And then Tuesday is the quiz number 3, which includes this chapter here. Okay. We're going to talk about acids and bases, and you're probably familiar with a lot of acids already, just from everyday use. Italian dressing has a lot of acid. It's called acetic acid. All right, but remember, excuse me, something make me kind of sneezy. Remember, hydrogen is in group 1. Okay, how many valence electrons can hydrogen have? Or does hydrogen have? 1. Okay, and having 1 valence electron, hydrogen, and that's why they put it in group 1, because it has 1 valence electrons, can, like metals, lose that valence electron. And when it loses that valence electron, guess what it makes? It makes an ion, okay, with a plus charge right here. This is called, we call that a proton, P-R-O-T-O-N. That is a hydrogen atom that had lost that valence electron, okay? That is what produces an acid. Anything that produces a proton, okay, which is an H+, is acidic in nature, okay? They tend to taste sour, hence vinegar, lemon juice, very sour tasting. They're very corrosive. They will react with metal with time and break it down, okay? Your stomach right now is loaded with H+ ions. That's why our stomach's so acidic. Okay. Now, if we wanted to test for an acid, there is such a thing called blue litmus paper, and it's either a yes or no answer with this paper. You have blue litmus paper, and if you put in a solution that's acid, it turns red. That's all it tells you. It's just red. That means that it's an acid. Very quick test to see acidity. If you put that blue litmus paper and it stays blue, then it's basic. It's nothing happens. It's not acidic. All right. So protons. Let me do this. That these are called protons. It's a hydrogen atom that has lost its valence electron. Okay. Now, going to the next slide where we got bases. OH negative. That's that polyatomic ion that's in your table, periodic table. Okay. Anything that produces, and this is called hydroxide. Anything that produces a hydroxide ion, okay, is a base. Tums, for example, calcium hydroxide. It's a base. Baking soda, and during this reaction, is a base. It produces hydroxide ion. Okay. Some other ones around there, but generally, I wouldn't recommend them. But they taste kind of bitter. Oh, liquid plumber. Liquid plumber is a good example. Put it in your drain because it's clogged up. It's a base. It's a very strong base. Don't recommend tasting it, but if you did, it'd be bitter and kind of a chocolatey texture. It feels, when you put it in your fingers, kind of soapy and slimy. That's not the chemical. If you get something like Drano in your hands or liquid plumber in your hands and it's slimy, it's because the sodium hydroxide is breaking down the tissue of your skin. So be careful. There's a lot of makeup stuff out there that you do put on your face because it's supposed to peel your skin. What it's doing is literally reacting and breaking down the skin tissue. So be careful with that. All right. For litmus paper, we not only do we have blue litmus paper, but we have red litmus paper. Again, if you put that red litmus paper in the solution and it turns blue, then you have a base solution. Okay. Now, there's one definition. We're going to talk about two definitions of acids and bases. The first one is called the Arrhenius acid. Okay, let me get rid of that. Arrhenius acid. And by definition, any chemical that produces a proton, H plus, in solution is classified as a Arrhenius acid. Okay. And anything that produces a hydroxide ion is considered a base, Arrhenius, specifically Arrhenius base. And this definition worked pretty good for a while, but then there's other chemicals that have nothing to do with producing hydroxides, and it can be base. And so we had to do an additional definition. Okay, and we'll talk about that in a second. Now, what happens when you take Tums because you have a little bit of an acid going on, you're a little acidity in your stomach? You are neutralizing the acidity. Okay, and so here you have a base, sodium hydroxide, with hydrochloric acid. Okay, the hydroxide reacts with the proton to create water. And that's how you neutralize. And then the counter ions that are there associated with it just make the salt. Okay, so this is your first type of chemical reaction that you're being introduced to. There are 6 types, and this is one of them, neutralization reaction. So next time you drink Tums, this is what's happening in your stomach. You lower the acidity content in your stomach, but you don't want to lower it too much because this is important to have a very low pH in your stomach for things to work properly. Okay. All right. So our second definition is called a Bronsted-Lowry acid or base. Now, how they differ from the Arrhenius? Well, the first definition of an acid is basically the same. The Bronsted-Lowry says that any compound that donates or produces a proton is an acid. So that's where the two definitions are the same. Where they differ is when it comes to the base. Okay. And the Bronsted-Lowry definition says that any compound that accepts that proton is a base. So what we have here is ammonia, NH3. Notice that has nothing to do with hydroxide. The hydroxide definition from Arrhenius, nothing's produced here. But I want you to remember about the lone pair of an ammonia. Remember, there's 2 lone pair here on the nitrogen, making it very polar. Remember, if we do the Lewis dot structure, you get 2 lone pair there. The proton, remember, hydrogen had 1 valence electron and it lost that electron. And so that orbit, the 1s1 orbit, now is empty. It's still there, but it's empty. Nitrogen has 2 lone pairs of electrons. And what it essentially does is it takes those 2 lone pairs of electrons and inserts them into the proton that has that orbital there but missing. So they share those electrons to create this cation. And that you'll find that cation in the polyatomic ions. And that is NH4 plus. Okay. And so here ammonia is a base because it accepted the proton from an acid. Now here's something else. 90-some% of the time when you see hydrogen written first in the formula, you can probably be 99% of the time you can probably be assured that we're talking about an acid. Okay. So that's another hint for you when you start looking at these compounds. Okay, so we got hydrogen written first. Flag comes up, I'm dealing with an acid. Sure enough, HCl is a very strong acid. Okay, let me clear some of this. So the 2 definitions, Arrhenius acid produces a proton, Arrhenius base produces a hydroxide. The Bronsted-Lowry definition, an acid produces a proton or donates it, same thing really. They differ in the base. The Bronsted-Lowry base is any chemical that will accept that proton. Okay. So anyway, I'm a little bit over 3 o'clock, so maybe we'll stop it here. And then come Monday, I would go ahead and look at the video on the website about this chapter. You know, I planned to finish it by today, but it didn't work out very well. So we will knock it out on Monday. But do listen to Dr. Kim's video on this particular topic. We won't have many more slides to do. The other ones are just very quick. So we'll have plenty of time on Monday to knock it out. So other than that, you have any questions, comments, concerns, stay safe out there. It's getting a little bit crazy with the COVID. And so be safe out there.